What if everything you've ever imagined about the edge of the universe is gently mistaken? Not a wall, not a cliff, not a final star fading into darkness. For thousands of years, humanity has looked up at the night sky and quietly wondered where it all ends. But modern cosmology whispers something far stranger. There may be no edge at all. The part of the universe we can observe stretches about 93 billion light-years across. That number sounds enormous, and it is. Yet even that vast sphere may be only a small patch of something far greater, something that continues beyond what light has had time to show us. Tonight, here on Velarin's Sleepy Space Mysteries, we're not simply asking where the universe ends. We're asking whether the very idea of an ending dissolves when we see the cosmos through the lens of relativity, expansion, and the oldest light in existence. That ancient glow, called the cosmic microwave background, now rests at a temperature of about 2.725 degrees above absolute zero. So faint, so gentle, yet it carries the memory of the early universe. In the first instant after the Big Bang, space expanded at a speed almost impossible to imagine. In far less than a trillionth of a trillionth of a trillionth of a second, that's 1 divided by 10 followed by 32 zeros, the universe stretched enormously, smoothing itself out. Today, galaxies drift apart at about 70 kilometers per second for every megaparsec of distance. In simple terms, the farther a galaxy is, the faster it appears to move away, not because it is racing through space, but because space itself is expanding. There are regions more than 16 billion light-years away that are already beyond contact. Light leaving them today will never reach us, not because it is too weak, but because the space between us grows too quickly. So stay with me, because the edge we're searching for may not be a location in space at all. It may be a boundary in time. If these quiet cosmic journeys bring you peace, gently subscribe, like, turn on the notification bell, and consider joining our membership so these night explorations can continue. And before we drift deeper, tell me in the comments where you're listening from. I'd love to see how far across this expanding universe this story has traveled tonight. In 1917, Albert Einstein took a step that quietly dissolved the old picture of a universe with edges. Until then, many still imagined space as a vast stage that might, somewhere far beyond the last visible star, simply stop. Einstein's equations of general relativity suggested something far stranger. The universe, he proposed, could be finite yet unbounded. To understand what that means, imagine the surface of a sphere. It has a limited area. You could, in principle, measure it. Yet there is no edge where you fall off. You can walk in any direction without ever encountering a boundary. Now lift that idea 1 dimension higher. Instead of a 2-dimensional surface curved in 3 dimensions, imagine a 3-dimensional space curved in a 4th spatial dimension. In such a geometry, traveling endlessly in one direction would not lead to a cliff or wall. Given enough time, you would eventually return to where you began, not because you turned around, but because space itself curved back on itself. This idea did not emerge from poetic speculation. It arose from mathematics. In general relativity, gravity is not described as a force pulling objects together. It is described as curvature in spacetime. Matter and energy tell spacetime how to curve, and curved spacetime tells matter how to move. Planets follow the straightest possible paths called geodesics, but those straight paths exist within a curved geometry. If enough mass and energy fill the universe, the large-scale geometry itself can bend. The crucial quantity is the overall density of the cosmos. If the density is high enough, space curves positively like the surface of a sphere. If it is lower, space may be flat or even negatively curved like a saddle. For decades, this remained an open question. Was the universe closed and curved back on itself, or open and endless? The answer required measuring geometry on the largest possible scales. That measurement came from the faint afterglow of the early universe, the cosmic microwave background, glowing today at about 2.725 Kelvin above absolute zero. Tiny variations in its temperature, differences of only millionths of a degree, encode the curvature of space. When missions such as the Wilkinson Microwave Anisotropy Probe and later Planck mapped this radiation with extraordinary precision, they revealed something astonishing. The universe is remarkably flat. Any overall curvature is constrained to less than roughly 0.4%. Flat does not automatically mean infinite. It means that within the observable region about 93 billion light-years across, space behaves as if Euclidean geometry applies. Parallel lines do not noticeably converge or diverge. The angles of enormous cosmic triangles add up, within measurement error, to 180 degrees. Yet this near flatness carries a deeper implication. It aligns almost perfectly with inflation theory. According to inflation, in the first tiny fraction of a second after the Big Bang, specifically within about 10 to the minus 32 seconds, space expanded exponentially. Distances increased by a factor of at least 10 to the 26. To speak that number slowly, that is 1 followed by 26 zeros. Such an expansion would stretch any initial curvature so dramatically that even if the universe began strongly curved, it would appear almost perfectly flat today, the way a small patch of Earth's surface appears flat to someone standing on it. This is where the concept of an edge begins to dissolve. The observable universe extends about 46.5 billion light-years in every direction. That distance is larger than the universe's age in years because space has been expanding while light traveled toward us. Yet that 46.5 billion light-year radius does not mark a physical boundary. It marks a horizon. Light from regions farther away has simply not had enough time to reach us since the universe became transparent about 380,000 years after the Big Bang. Beyond that horizon lies more universe, perhaps vastly more, but it is hidden from view by time itself. So the edge we often imagine is not a wall in space. It is a limit in visibility. Picture again a tiny ant walking across a globe. The ant moves forward in what feels like a straight line. It never encounters a border. It never sees curvature directly. From its perspective, the world stretches on and on. Only from a higher vantage point does the spherical nature become clear. We may be in a similar position. Embedded within 3 spatial dimensions, we cannot step outside to see whether our universe curves in a higher dimension. We infer its shape only through subtle patterns in ancient light. And there is another complication. one that makes the journey around a curved universe even more elusive. Space is not static. It is expanding. Even if the cosmos were shaped like a vast three-dimensional sphere, the scale of that sphere is increasing with time. Imagine drawing a circle on the surface of a balloon and then inflating the balloon steadily. A traveler walking along that circle might try to complete a full loop. But if the balloon expands quickly enough, the circumference grows faster than the traveler can traverse it. The path lengthens continuously. In principle, the loop exists. In practice, it may never be completed. In our universe, expansion is governed by the Hubble constant, roughly 70 kilometers per second per megaparsec, meaning that for every 3.26 million light-years of distance, recession speed increases by about 70 kilometers per second. On the largest scales, that stretching can outpace any attempt at circumnavigation. Even light, moving at 299,792 kilometers per second, cannot catch up to regions receding beyond the cosmic event horizon. So even if space does loop back on itself, the stretching metric could prevent any signal, any traveler, from ever finishing the circuit. The geometry may be closed. The experience may still be endless. And so we are left in a universe that might be finite in volume yet functionally without boundary. A cosmos where the edge is replaced by curvature, and curvature is hidden by expansion. If you are still drifting through this curved expanse with me, type 1 in the comments so I know you are traveling within this geometry without walls. To feel how radical this geometry truly is, we have to let go of the instinct that every container must sit inside something larger. In everyday life, a room has walls, a shoreline has an ocean beyond it, and even our planet floats within the larger arena of the solar system. So when we ask what lies beyond the universe, we are quietly assuming the universe is like a room with an outside. General relativity challenges that assumption at its root. The universe is not an object inside space. It is space. Asking what lies beyond it may be like asking what is north of the North Pole. The question dissolves not because it is foolish, but because the geometry does not allow it. In Einstein's 1917 cosmological model, he initially imagined a static universe, neither expanding nor contracting. To make his equations fit that picture, he introduced a cosmological constant, a term that balanced gravity on the largest scales. In that version, space could be finite yet unbounded, curving gently back on itself in perfect equilibrium. Although we now know the universe is expanding, the deeper geometric insight remains. Curvature does not require an edge. A three-dimensional hypersphere would have a finite volume, just as the surface of a sphere has finite area, but it would not contain any boundary you could touch. If you moved in what you believed was a straight line, you would simply trace a great circle through higher dimensional curvature. The key to detecting such curvature lies in cosmic triangles. Imagine selecting 3 distant galaxies and measuring the angles between them. In flat Euclidean space, those angles would add up to 180 degrees. In positively curved space, the sum would be slightly greater than 180 degrees. In negatively curved space, slightly less. The cosmic microwave background provides a natural version of this test. Tiny fluctuations in temperature represent sound waves that rippled through the early plasma. The physical size of those ripples is known from well-understood physics. By measuring how large they appear on the sky today, we can infer the geometry through which their light has traveled. If space were strongly curved, those patterns would appear stretched or compressed in a characteristic way. When scientists analyzed these patterns with increasing precision, first with COBE, then with WMAP, and later with Planck, the result was striking. The angular size of those primordial ripples matches what we expect in an almost perfectly flat universe. The deviation from exact flatness is smaller than about 0.4%. That is an extraordinary level of smoothness on scales of tens of billions of light years. It suggests that if the universe is curved back on itself, its radius of curvature must be far larger than the observable region. In simple terms, even if space eventually loops, the loop is so vast that we cannot detect its bend within our cosmic horizon. This is where inflation becomes central to the story. During inflation, space expanded faster than light in the sense that the metric itself grew exponentially. To say it slowly, within less than 1/10,000,000,000th of a trillionth of a trillionth of a second, distances expanded by a factor of at least 10 to the 26. A patch of space smaller than an atomic nucleus could have been stretched to macroscopic size. Any initial wrinkles and curvature would have been ironed out the way stretching a rubber sheet smooths tiny creases. That is why our universe appears so geometrically calm. Inflation did not just make space big. It made it uniform and nearly flat. Yet nearly flat does not mean perfectly flat. And that subtle distinction leaves open a profound possibility. Space could be finite, wrapping around in a topology more complex than a simple hypersphere. Cosmologists have explored shapes such as a three-dimensional torus, where traveling far enough in one direction could, in principle, bring you back from the opposite side. In such a topology, light from a single galaxy might traverse the universe more than once, creating multiple images of the same object in different parts of the sky. So far, no convincing evidence of such repeated patterns has been found, but the search continues in the delicate statistical fingerprints of the microwave background. Now imagine what it would mean to attempt a journey across such a cosmos. Suppose an advanced civilization built a spacecraft capable of traveling arbitrarily close to the speed of light. Even then, the traveler would face two immense obstacles. First, the sheer scale. The observable universe alone spans about 93 billion light-years in diameter. Second, the ongoing expansion. As the traveler moves forward, the space ahead continues to stretch. Regions beyond roughly 16 billion light-years are already receding faster than light due to cosmic acceleration. That does not violate relativity because nothing locally exceeds the speed of light. It is space itself that grows. But the practical consequence is profound. Some destinations are not just far. They are forever unreachable. So even if the universe is shaped like a closed surface in higher dimensions, the dynamic expansion may ensure that no path ever completes a loop. The geometry may promise return. The expansion may deny it. In this sense, the cosmos can be both finite and effectively endless. There is no wall to strike, no boundary to cross. yet also no guarantee that an eternal journey would ever bring you home. We might inhabit a structure that folds back on itself so subtly and stretches so relentlessly that its closure remains forever beyond experience. And as you drift with that thought, consider how different this is from the simple childhood image of a starry dome with an edge. The universe does not end in a barrier. Curves, expands, and hides its global shape behind horizons of time. There is a quiet elegance in realizing that the shape of the universe is not something we see directly, but something we deduce from whispers of ancient light. We cannot step outside the cosmos to photograph its curvature. We cannot float above it to watch it bend. Instead, we listen to subtle patterns left behind when the universe was only 380,000 years old, when matter and radiation parted ways and photons began their long, uninterrupted journey. Those photons, stretched by 13.8 billion years of expansion, now bathe us as microwave radiation. They form a spherical horizon around every observer, a glowing shell that marks the limit of what light can reveal. Inside that shell, geometry speaks softly through statistics. The early universe was filled with pressure waves moving through hot plasma, compressing and rarefying matter like sound traveling through air. The maximum distance those waves could travel before the universe became transparent is called the sound horizon. That scale is imprinted in the microwave background as a preferred size for temperature fluctuations. When we measure how large that scale appears on the sky, we are effectively measuring the curvature of space between us and that ancient surface. If space were strongly curved, the apparent size would shift noticeably. Yet it does not. It sits exactly where near-flat geometry predicts. But imagine if the curvature is not zero, only extremely small. A sphere of enormous radius can look flat over limited regions. The Earth itself feels flat beneath our feet because its radius is about 6,371 kilometers. Over a few kilometers, the curvature is imperceptible. In the same way, if the universe's radius of curvature is hundreds of billions or trillions of light years, then our 46.5 billion light-year observable radius samples only a tiny patch. Within that patch, straight lines behave as if they are straight forever. Only on scales far beyond our horizon would the bending reveal itself. This leads to a humbling thought. The global topology of the universe could be far more intricate than a simple infinite expanse. Space might connect back to itself through pathways we cannot observe. There are mathematically consistent models in which space is multiply connected, meaning that traveling far enough in one direction would bring you back to your starting point, but from a different angle. In such a universe, the same galaxy could, in principle, appear in multiple locations in the sky, its light having wrapped around the cosmos along different routes. Detecting such patterns would require identifying matching structures separated by enormous angles, like finding identical fingerprints hidden in a cosmic mosaic. So far, no clear repetition has been confirmed, but the absence of evidence does not yet close the possibility. Meanwhile, expansion continues to reshape the practical meaning of distance. The observable universe extends about 46.5 billion light-years in every direction, yet the age of the universe is 13.8 billion years. That apparent contradiction arises because space has stretched while light was in transit. When a photon began its journey, the region that emitted it was much closer. Over billions of years, the intervening space expanded, carrying that region farther away. By the time the photon arrives, its source is vastly more distant than the simple product of time and the speed of light would suggest. This stretching also affects any hypothetical journey across a curved cosmos. Suppose the universe is closed like a three-dimensional sphere. In a static version, a traveler moving forever in one direction would eventually return home. But our universe is not static. Its scale factor, the number that describes how distances expand with time, is increasing. And not merely increasing, but accelerating under the influence of dark energy. That acceleration creates a cosmic event horizon at roughly 16 billion light-years. Beyond that distance, regions recede so quickly that light emitted today will never reach us, no matter how long we wait. If you imagine walking along the surface of a balloon while it inflates faster and faster, you may sense the paradox. The path you are trying to complete grows longer as you move. Even if the surface eventually loops, the circumference increases without bound. You chase a closure that recedes ahead of you. In such a scenario, the universe could be finite in total volume yet eternally untraversable in practice. The loop exists mathematically, but no traveler could complete it because expansion stretches the route faster than any signal or spacecraft could follow. This is why the idea of an edge becomes increasingly abstract. It is not a cliff at the boundary of stars. It is not a wall of darkness. It is a limit defined by light travel time and expansion history. The true boundary we encounter is the horizon beyond which information has not yet reached us and may never reach us. Even if space curves back on itself on scales far beyond our sight, the expansion ensures that large portions of that structure remain causally disconnected. So we inhabit a cosmos where geometry without walls replaces the comfort of boundaries. Finite does not imply fenced. Curved does not imply closed in any accessible sense. The universe may loop in dimensions we cannot visualize, yet its stretching fabric prevents us from ever confirming the full circuit by travel alone. All we have are the faint temperature ripples of ancient radiation and the redshift of distant galaxies, subtle clues that guide us through this vast geometric puzzle. And in that puzzle, the edge is not a place waiting to be reached. It is a concept that fades as our understanding of space deepens. If we step back and allow the numbers to settle gently in the mind, a quiet picture begins to form. The observable universe spans about 93 billion light-years in diameter, meaning 46.5 billion light-years in every direction from where you sit right now. That sphere is not centered on Earth in any privileged way. Every observer anywhere in the cosmos would measure a similar sphere around themselves. Each would see light that has had time to arrive since the universe became transparent. Each would stand at the center of their own horizon. This symmetry is not a coincidence. It is built into the structure of expanding spacetime itself. Now imagine that this vast sphere is only a local patch of a much greater whole. Beyond the 46.5 billion light-year horizon lies more universe, perhaps infinitely more, perhaps a closed curvature that eventually reconnects. But the light from those regions has not reached us. Not because there is a barrier blocking it, but because time and expansion have not permitted it. The universe is 13.8 billion years old, and light travels at 299,792 kilometers per second. Those two facts alone impose a limit. Add in cosmic expansion, and that limit stretches even further outward in distance while remaining fixed in time. This is why the edge is really a boundary in visibility. It is a surface defined by causality. If a galaxy beyond our horizon were to emit a flash of light today, that light might never reach us, because the space between us and that galaxy is expanding too quickly. In that sense, the horizon is not static. It evolves. Some regions that were once within communicable range may eventually drift beyond it as accelerated expansion continues. The universe does not end at that horizon. It simply becomes unreachable. Here the ant on the globe analogy deepens. Picture the ant again, walking steadily in what it believes is a straight line. It has no awareness of curvature beneath its feet. It does not sense that the path it calls straight is actually part of a great circle. Now imagine that the globe beneath the ant is slowly inflating. The ant keeps walking, yet the surface stretches under it. The route back to its starting point lengthens continuously. Even though the globe remains finite, the ant may never complete the loop because the surface expands faster than it can traverse. In our universe, the stretching is governed by the scale factor, a quantity that describes how distances grow with cosmic time. Observations show that this growth is accelerating due to dark energy, which makes up about 68% of the total energy density of the cosmos. Dark energy does not clump like matter. It behaves more like a property of space itself, causing expansion to speed up. As a result, the separation between distant galaxies increases at an ever-growing rate. This acceleration strengthens the horizon effect. Regions already far away become permanently isolated. So even if space loops back on itself on scales vastly larger than what we can see, the dynamic stretching of that loop may prevent any complete circuit. A traveler could set out in a single direction and continue indefinitely, yet never encounter an edge and never return home. The geometry would allow closure in principle. The expansion would forbid it in practice. Finite yet unbounded becomes not just a mathematical phrase but a lived cosmic condition. There is something deeply humbling in this realization. For centuries, humans feared falling off the edge of the world. Later, we imagined the universe might have a final wall, a place where stars stopped and darkness began. Modern cosmology replaces that image with something subtler and more profound. There is no wall. There is curvature. There is expansion. There is a horizon defined by the finite age of the universe and the finite speed of light. Beyond that horizon lies more reality, but not necessarily an outside. And if we pause with that thought, we begin to see how the question itself transforms. Instead of asking where the universe ends, we ask how geometry behaves on scales beyond measurement. Instead of picturing a boundary in space, we consider limits in knowledge. The edge is not a physical cliff, but a conceptual one. It marks the point where our observations run out, where photons have not yet arrived, where the curvature may exist but remains too subtle to detect. We may indeed be like the ant, embedded within a higher dimensional structure too vast to perceive directly. We infer its shape from faint patterns, from temperature variations of 1 part in 100,000, from recession speeds that increase by about 70 kilometers per second for every megaparsec of distance. Each number is a clue. Each measurement tightens the constraints on curvature. Yet none reveals the global shape with absolute certainty. And so we drift in a cosmos that may be finite yet has no walls, curved yet appears flat, connected yet forever expanding. The journey outward does not end in collision with a border. It fades into horizons of time and visibility. The universe does not stop. It simply continues beyond what we can currently see. If you are still traveling through this geometry without walls, let that thought settle gently. We are not confined by edges. We are embedded within curvature, carried by expansion, and surrounded by a horizon that marks not the end of space, but the reach of light. There is a quiet paradox at the heart of this geometry without walls. On one hand, the equations of general relativity allow a universe that is finite in total volume, gently curved like the three-dimensional surface of a four-dimensional sphere. On the other hand, every observation we make suggests that, within the region we can measure, space is astonishingly flat and relentlessly expanding. These two facts are not in conflict. They simply describe different layers of reality. The global shape that may exist far beyond our horizon, and the local behavior that governs everything we can see. When we say the observable universe extends 46.5 billion light-years in every direction, we are describing a sphere defined by light travel time and expansion history. That sphere is not the whole cosmos. It is a window. Beyond it, space continues, perhaps forever, perhaps curving so subtly that its closure lies trillions of light-years away. If the universe is closed, its radius of curvature must be vastly larger than the observable region. Imagine standing on a plane so immense that even after walking for thousands of kilometers, the ground beneath you feels perfectly flat. Only from a perspective impossibly far above could you see the curvature. Yet the expansion complicates this image further. The scale factor of the universe grows with time, and because dark energy drives accelerated expansion, that growth is not slowing. It is speeding up. Distances between galaxies not gravitationally bound increase faster and faster. The Hubble constant, roughly 70 kilometers per second per megaparsec, tells us how recession speed scales with distance today. But over cosmic time, that relationship evolves as the influence of dark energy becomes dominant. The result is a future in which more and more galaxies slip beyond our event horizon, not because they hit an edge, but because the space between us and them stretches too quickly for light to bridge. This means that even if the universe does curve back on itself, large portions of that curvature may remain forever inaccessible. There could be a grand cosmic loop, but expansion may stretch it faster than any traveler, or even any photon could complete the circuit. The idea of returning to your starting point by traveling in a straight line becomes less a journey and more a mathematical property, hidden behind accelerating distances. Finite does not guarantee reachable. Closed does not guarantee connected in practice. It is also possible that the universe is truly infinite, flat not just locally but globally. Current measurements cannot decisively distinguish between an exactly flat infinite cosmos and an almost flat but very large closed one. The difference may lie far beyond the scale we can observe. If the curvature radius is hundreds of times larger than the observable universe, its effects would be indistinguishable from perfect flatness within our horizon. In that case, the universe could extend without bound, stretching endlessly in every direction. But even then, there would still be no edge in the sense of a wall. Infinite space has no boundary. You would never reach a final star beyond which nothing exists. What makes this vision so different from earlier human imaginings is that it replaces solid boundaries with relational limits. The only meaningful edges are horizons defined by causality and time. The cosmic microwave background forms one such boundary, a glowing shell marking the moment when the universe became transparent about 380,000 years after the Big Bang. Beyond that shell lies earlier time, not empty space. Likewise, the event horizon marks regions from which signals emitted today will never reach us. Beyond it lies more universe, but forever out of contact. In this way, the edge becomes a dynamic concept. It shifts as the universe ages. Every year, light from slightly more distant regions has time to reach us, expanding the observable sphere by roughly 1 light-year in radius. Yet, at the same time, accelerated expansion ensures that some regions drift irreversibly beyond reach. The horizon grows in one sense and shrinks in another. Geometry and expansion work together to define what is knowable. If we return to the ant on the globe, we see that its experience contains no hint of an edge. It moves unaware of curvature, unaware of higher dimensions. This world feels open and continuous. We may be in the same situation. The global topology of the universe could be curved, connected, perhaps even looping in ways our three-dimensional intuition struggles to imagine. But from within, all we encounter are distances, redshifts, and horizons. No walls, no cliffs, only gradual fading into invisibility. And perhaps that is the most profound shift of all. The universe does not end in a boundary you can touch. It ends for us in the limits of observation. The geometry may be finite yet unbounded, infinite yet edgeless, curved yet indistinguishable from flat. Whatever its ultimate shape, it does not present a border to crash into. It offers instead a subtle invitation to understand curvature, expansion, and time. So as you drift at the edge of visibility, remember that the cosmos is not a room with an outside. It is a self-contained geometry, expanding, stretching, and perhaps gently looping beyond our sight. The edge is not out there waiting to be reached. It is the horizon of light, the boundary of causality, and the quiet reminder that space itself may have no walls at all. In 1929, Edwin Hubble measured something so quiet and so profound that it changed the meaning of distance itself. By comparing the faint glow of distant galaxies to their spectral lines, he discovered that almost every galaxy beyond our local group is receding from us. More astonishing still, the farther away a galaxy is, the faster it appears to be moving away. This simple proportional relationship became known as the Hubble-Lemaitre law. Today, we describe the rate of this expansion using the Hubble constant, a number that tells us how quickly space stretches per unit distance. Its value is close to 70 kilometers per second per megaparsec. In gentle terms, that means for every 3.26 million light-years of distance, a galaxy appears to recede about 70 kilometers per second faster. At 10 megaparsecs, that becomes roughly 700 kilometers per second. At 100 megaparsecs, 7,000 kilometers per second. Distance itself multiplies motion. Yet there is an important subtlety here. The galaxies are not blasting outward through empty space like debris from an explosion. Nothing is flying away from a central point. Instead, space itself is expanding. The metric that defines distance between 2 points slowly grows with time. Imagine marking 2 dots on a sheet of elastic fabric. If the fabric stretches, the dots separate even if they never move across the surface. That is the essential picture of cosmic expansion. Galaxies remain largely at rest within their local regions, gravitationally bound to their neighbors, but the fabric beneath them lengthens. This distinction resolves a paradox that once seemed impossible. Einstein's special relativity tells us that nothing can move through space faster than the speed of light, which is precisely 299,792 kilometers per second. That limit applies to local motion, to objects passing one another in the same region of space. But general relativity allows the geometry of space itself to evolve. There is no speed limit on how fast the distance between 2 faraway galaxies can grow if that growth is due to expansion of the metric itself. As a result, at sufficiently large distances, galaxies recede from us at effective speeds greater than light. This does not violate relativity, because they are not overtaking light in their local neighborhood. The space between us and them is stretching. If the distance is large enough, the rate of that stretching exceeds 299,792 kilometers per second. From our perspective, those galaxies slip away faster than any signal could chase them. The Hubble constant itself is not known with perfect precision. Measurements based on nearby supernovae and Cepheid variable stars suggest a value around 73 kilometers per second per megaparsec. Measurements based on the cosmic microwave background suggest closer to 67. This small but persistent difference is called the Hubble tension. It may hint at subtle new physics in the early universe, or perhaps refinements in our calibration methods. For now, the expansion rate lies within that narrow band, gently shaping every cosmic distance we measure. If we follow the logic of expansion outward, we encounter a boundary not of matter, but of causality. There exists what cosmologists call a cosmic event horizon. It lies roughly 16 billion light-years away in present-day distance. Beyond that radius, regions of space are receding from us so rapidly that any light they emit today will never reach Earth. Not in a trillion years, not ever. The stretching of space outpaces the light's attempt to cross it. This horizon is not the same as the observable universe's edge. The observable universe extends about 46.5 billion light-years in every direction, forming a sphere roughly 93 billion light-years across. We can see light that was emitted long ago from regions that are now far beyond 16 billion light-years away. But that light began its journey when those galaxies were closer and the expansion rate relative to their distance was smaller. The event horizon concerns what can ever influence us from this moment forward. So we live within layers of visibility. Some galaxies we see today are already beyond the event horizon. We observe their ancient light, but any message they send now will never arrive. It is as though we are reading letters from civilizations already carried irreversibly beyond contact by the expanding sea of space. The deeper we look into space, the further back in time we travel. This is not metaphorical. Light has a finite speed. If a galaxy is 1 billion light-years away, the light we see tonight left that galaxy 1 billion years ago. When we observe extremely distant galaxies with redshifts greater than 13, we are seeing light emitted when the universe was less than 300 million years old, only about 2% of its current age of 13.8 billion years. Those galaxies today are far more distant than 13 billion light-years because the universe has expanded dramatically while their photons were in transit. This leads to a layered vision of reality. Nearby galaxies show us relatively recent cosmic history. Farther galaxies reveal earlier epochs. Beyond them lies a faint, nearly uniform glow. The cosmic microwave background, released about 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely. That glow corresponds to a redshift of about 1100 and forms a spherical shell around us in every direction. The edge we approach is not a wall in space. It is a horizon shaped by time, expansion, and the finite speed of light. And as space continues to stretch, that horizon subtly evolves, redefining what can be known and what will remain forever beyond reach. To understand why some galaxies appear to outrun light, we have to gently separate two ideas that are often tangled together: motion through space and expansion of space. If a spacecraft passes you at 90% of the speed of light, relativity strictly governs that motion. No matter how powerful its engines, it cannot locally exceed 299,792 kilometers per second. That limit is woven into the structure of spacetime itself. But when we look at a galaxy billions of light-years away, we are not measuring how fast it is flying through its local surroundings. We are measuring how quickly the distance between us and that galaxy increases because the scale of the universe changes with time. The mathematical description of this comes from solutions to Einstein's field equations, in which a quantity called the scale factor grows as the universe evolves. When the scale factor increases, every large distance increases with it. If the separation is great enough, the rate of change of that separation can exceed the speed of light, not because anything is breaking a rule, but because the rule never applied to global expansion in the first place. Imagine standing on a vast rubber sheet marked with evenly spaced dots. As the sheet stretches uniformly, each dot sees all others drifting away. The farther a dot is, the faster it recedes. No dot is special. No dot sits at the center. This is precisely how expansion looks from any galaxy in the universe. From our vantage point in the Milky Way, distant galaxies obey the Hubble-Lemaitre relation. From a galaxy 10 billion light-years away, the pattern would look the same. They would see us receding, along with nearly everything else. Expansion has no preferred location. It is a property of space itself. Now consider what happens to light traveling across this stretching fabric. A photon leaving a distant galaxy begins its journey when the universe is smaller. As it moves forward, the space it crosses expands beneath it. Its wavelength stretches along with space. This is cosmological redshift. The greater the expansion during the photon's travel time, the longer its wavelength becomes. If the wavelength doubles, the universe has doubled in scale during that interval. If the wavelength stretches by a factor of 14, as in galaxies at redshift 13, then the universe expanded 14-fold while the light was en route. The photon does not tire or slow down. It always moves locally at the speed of light, but the distance it must cross increases as it travels, like walking on an escalator that is moving downward while you climb upward. This interplay creates several distinct horizons. The most familiar is the particle horizon, which defines the boundary of the observable universe. Because the universe is 13.8 billion years old and light has a finite speed, there has only been a limited amount of time for signals to reach us. Yet because expansion stretches distances while light travels, the present-day distance to the most remote visible regions is about 46.5 billion light-years in every direction. That forms the 93 billion light-year diameter of the observable universe. It is not the age of the universe multiplied by the speed of light. It is larger because space has expanded throughout the entire journey. Then there is the cosmic event horizon, subtler and more final. Due to the accelerating expansion driven by dark energy, there are regions whose present separation from us is so large that light emitted now will never overcome the growing gap. The expansion accelerates the stretching of space over time. Even if a photon sets out toward us at full light speed, the space between us and its origin grows too quickly. It falls eternally short. The event horizon marks the boundary between regions that can still influence our future and regions that are forever causally disconnected. Acceleration is the key here. If gravity from matter alone governed expansion, the rate would gradually slow over billions of years. But observations of distant supernovae in the late 20th century revealed that expansion is speeding up. Dark energy, which accounts for roughly 68% of the universe's total energy density, acts like a uniform pressure intrinsic to space. As space expands, more space appears, and with it more dark energy. The effect compounds, gently but relentlessly pushing galaxies apart at an ever-increasing rate. Over immense timescales, this acceleration ensures that more and more galaxies will slip beyond our event horizon. Even now, many galaxies we observe are already receding faster than light in terms of effective distance growth. We can still see them because the light reaching us today was emitted when they were closer and the expansion rate across that smaller separation was not yet insurmountable. But if those galaxies emit a signal today, it will never arrive. Their future light is lost to us. We live in a narrow era of cosmic history when the universe is old enough for complex structure to exist, yet not so old that acceleration has erased most of the visible cosmos. The deeper we peer, the more ancient the light becomes. Observations of galaxies at extreme redshift reveal structures that existed when the universe was only a few 100 million years old. Beyond them lies the cosmic microwave background, the afterglow of a time 380,000 years after the Big Bang, when atoms first formed and light could finally travel freely. That surface is not a wall of matter. It is a boundary in time. Before it, the universe was a hot plasma opaque to radiation. No optical or infrared telescope can see beyond that era because photons themselves could not travel in straight lines earlier than that moment. So the illusion of faster-than-light motion is born from geometry. Galaxies are not defying Einstein. They are being carried by a metric that grows. The universe reveals itself not as an explosion into emptiness, but as a continuous stretching of the distances that define it. And as that stretching continues, the horizons that shape our cosmic view quietly evolve, redrawing the limits of what can ever be known. When we speak about horizons in cosmology, it helps to imagine that we are not standing in the center of a vast room, but inside a sphere of light whose radius is determined by time. Every direction we look, we see deeper into the past. Nearby stars show us years-old light. Nearby galaxies show us millions of years-old light. Distant galaxies reveal billions of years of history. And at the farthest limit visible to electromagnetic radiation, we encounter the cosmic microwave background, released when the universe was about 380,000 years old. That faint glow marks a boundary not in space, but in time. It is the oldest light that can ever reach us through ordinary observation. If the universe had not expanded, the story would be simpler. Light emitted 13.8 billion years ago would now lie 13.8 billion light-years away. But because space has stretched during the journey of every photon, the present-day distance to the region that emitted that ancient light is far greater. The light from the cosmic microwave background has been traveling for 13.8 billion years, yet the matter that emitted it is now about 46.5 billion light-years away. That factor arises because the scale of the universe has increased dramatically while the photons crossed it. The expansion is not a single burst long ago. It is an ongoing process, quietly lengthening every large separation. This leads to a layered structure of visibility. Imagine concentric shells around us. The innermost shell contains galaxies whose light left only recently in cosmic terms. Slightly farther shells contain galaxies seen as they were billions of years ago. The outermost luminous shell is the microwave background itself, corresponding to a redshift of about 1100. Each shell is a slice of cosmic history. As telescopes grow more powerful, we do not push outward into new territory in space. We peel back earlier chapters in time. Beyond the microwave background lies an era when the universe was filled with a dense, ionized plasma. Photons scattered constantly off free electrons. Light could not travel in straight paths. The universe was opaque. Even if there were structures or fluctuations earlier than 380,000 years after the Big Bang, their light is forever hidden from us. To probe that epoch, we must rely on indirect messengers such as subtle patterns imprinted in the microwave background or perhaps gravitational waves from the earliest fractions of a second. The horizon at redshift 1100 is therefore a limit imposed by physics itself. Now return to the idea of faster-than-light recession. Consider a galaxy whose present distance from us is 30 billion light-years. Because the Hubble expansion rate increases with distance, the effective recession speed associated with that separation can exceed the speed of light. Yet the light we currently observe from that galaxy was emitted when it was much closer, perhaps only a few billion light-years away, and the expansion rate across that smaller distance was less extreme. The photon began its journey in a universe with a smaller scale factor. As it traveled, space stretched. Its wavelength lengthened. The galaxy's present position moved far beyond what the original light travel time would suggest. This means the map of the universe is dynamic. The distances we assign today are not the distances that existed when the light we see was emitted. Cosmologists carefully distinguish between light travel distance, comoving distance, and proper distance. Light travel distance is simply how long the photon has been in motion multiplied by the speed of light. Comoving distance factors out the expansion and represents separation in coordinates that expand with the universe. Proper distance changes with time as the scale factor evolves. When we say a distant galaxy is now more than 30 billion light-years away, we refer to its present proper distance, not the distance when its light began the journey. The cosmic event horizon introduces a further subtlety. Because dark energy drives accelerated expansion, there exists a maximum distance from which signals emitted now can ever reach us in the future. That boundary is closer than the outer edge of the observable universe. Roughly speaking, it lies around 16 billion light-years in present proper distance. Regions beyond that are already so remote, and their separation is growing so quickly, that any photon emitted today will never close the gap. They are not hidden by dust or blocked by walls. They are simply carried away by expansion faster than light can compensate. Over immense stretches of time, this has dramatic consequences. Galaxies not gravitationally bound to us will gradually cross that event horizon. First, their light will grow more redshifted and faint. Then, after sufficient acceleration, new light they emit will never reach us at all. In trillions of years, observers in our galaxy might see only the remnants of the local group, with all other galaxies vanished beyond reach. The universe would appear static and empty, even though expansion continues relentlessly beyond their horizon. All of this arises from the simple fact discovered in 1929. The universe expands in proportion to distance. That proportionality, combined with the finite speed of light and the presence of dark energy, produces a cosmos structured by horizons. We inhabit a bubble of visibility whose radius is determined by age and expansion. We are surrounded not by a physical boundary, but by limits imposed by time. The illusion of superluminal motion, the existence of unreachable regions, and the layered archive of cosmic history all flow from that geometry. The edge is not a cliff in space. It is a horizon drawn by the interplay of expansion and light, ever shifting yet always finite. If we slow down and picture the universe as it truly behaves, the most unsettling realization is not that it expands, but that expansion reshapes what is possible. Every second that passes, more distant regions drift beyond the boundary of what can ever influence us. The cosmic event horizon is not fixed in moving coordinates. It is tied to the future evolution of expansion. Because dark energy drives acceleration, there are galaxies whose present light will never reach Earth, no matter how long the universe endures. Even if humanity survived for trillions upon trillions of years, even if we built detectors as large as galaxies themselves, there would still be regions forever silent to us. This creates a subtle distinction between what we see and what we can ever see. The observable universe contains everything whose light has already had time to reach us since the cosmic plasma became transparent. That sphere has a present radius of about 46.5 billion light-years. But the event horizon is smaller, around 16 billion light-years in present proper distance. Objects currently beyond that smaller radius are already beyond future communication. We may see their ancient glow, but we will never witness anything they do from this moment forward. Their present and future histories are sealed off from ours. The reason is rooted in the behavior of the scale factor, the mathematical function that describes how cosmic distances grow. In a universe dominated only by matter, gravity would gradually slow expansion. The scale factor would increase, but more and more slowly. In such a cosmos, light emitted from sufficiently distant regions could eventually overcome the stretching and arrive. But our universe is not matter-dominated forever. Dark energy becomes increasingly important as space grows. Unlike matter, whose density thins as the universe expands, dark energy maintains nearly constant density per unit volume. As more space appears, the total amount of dark energy increases proportionally. The effect is a self-reinforcing acceleration. Acceleration means that the expansion rate does not merely persist. It intensifies relative to distance. In practical terms, the gap between us and distant galaxies grows faster and faster. A photon emitted today from beyond the event horizon moves toward us at light speed locally. Yet the intervening space expands so rapidly that the total separation increases. The photon makes progress, but the finish line retreats even more quickly. Over infinite time, it never arrives. This is the true meaning of superluminal recession. No galaxy locally breaks the light speed limit. In its own neighborhood, nothing outruns a passing beam of light. But on cosmological scales, the integrated effect of expanding space allows the total separation between two widely spaced points to grow faster than light could traverse it. The limit of 299,792 kilometers per second remains untouched. What changes is the geometry that defines distance itself. When powerful telescopes observe galaxies at redshift greater than 10 or even 13, they capture light emitted when the universe was only a few 100 million years old. That light has traveled for more than 13 billion years. During that time, the universe expanded by more than an order of magnitude. The galaxies we see in those images are not where they appear to be in a simple static map. They are now far more distant than the light travel time alone would imply, often exceeding 30 billion light-years in present separation. The image is a snapshot of the past, superimposed on a geometry that has continued evolving. As we trace this pattern outward, we eventually reach the cosmic microwave background, the afterglow released when electrons combined with nuclei and the universe became transparent. That surface surrounds us in every direction, marking a redshift of roughly 1100. It is sometimes described as a glowing shell, but it is not a physical barrier. It is simply the farthest back in time that light can reveal. Beyond it lies an earlier era where photons could not travel freely. The edge, again, is temporal, not spatial. Put together, expansion and finite light speed create the illusion that we inhabit a central position inside a receding sphere. In reality, every observer in every galaxy would see a similar sphere centered on themselves. Each would measure distant galaxies moving away in proportion to distance. Each would encounter their own particle horizon and event horizon. There is no privileged location. The expanding metric guarantees this symmetry, and so the cosmos becomes an archive arranged in depth. The nearest layers record recent cosmic events. The intermediate layers show galaxies assembling, merging, igniting stars. The outermost luminous layer reveals the universe in its infancy. Beyond that lies a plasma epoch unreachable by light. Beyond the event horizon lies a future forever inaccessible. The edge is not a wall of matter or a cliff where stars stop. It is a horizon sculpted by time, expansion, and the unwavering speed of light. As long as space continues to stretch and dark energy continues to accelerate that stretching, horizons will define what can be known, quietly shaping the limits of our cosmic awareness. If we gather all these pieces together, a quiet but astonishing picture forms. The universe is not expanding into anything. It is not inflating into a pre-existing void. The distances between unbound structures increase because the metric that defines those distances evolves with time. When we say the universe expands, we are saying that the scale factor grows. Every large separation stretches in proportion. This simple rule, applied over 13.8 billion years, creates horizons, superluminal recession, and a layered record of cosmic history. The illusion of faster-than-light motion dissolves once we accept that speed limits apply locally, not globally. A galaxy 20 or 30 billion light-years away is not blasting through space at impossible velocity. In its own neighborhood, it drifts modestly relative to nearby matter. But the space between us and that galaxy has expanded so much, and continues to expand so rapidly, that the total proper distance increases faster than light could bridge it. If you imagine placing rulers end to end across the cosmos, the rulers themselves slowly lengthen. Measuring separation with those evolving rulers gives rise to recession speeds that can exceed light without any local violation of relativity. The cosmic event horizon adds a deeper emotional weight to this geometry. There are galaxies whose current light will never reach us. Not because they are hidden, not because of obstruction, but because the expansion of space will always outpace the photons they emit. Even if those galaxies shine brightly for trillions of years, even if new stars ignite and civilizations rise within them, their future stories are forever beyond our observational reach. We are connected only to their past, to photons that began their journey when the universe was smaller and the gulf between us was not yet insurmountable. In that sense, the universe is a one-way archive. We continuously receive ancient messages from distant epochs, but the flow of information is asymmetric. As dark energy drives acceleration, more regions cross beyond our event horizon. Their present becomes unreachable. Over unimaginable spans of time, even relatively nearby galaxy clusters will fade from view. Their light will stretch into wavelengths so long and faint that no conceivable detector could register them. The sky will empty not because matter disappears, but because expansion hides it behind an ever-receding causal boundary. Yet we live at a moment when the cosmic archive is still richly accessible. We can observe galaxies more than 13 billion years in the past. We can measure redshifts that reveal how dramatically the universe has grown. We can detect the cosmic microwave background, a nearly uniform glow at 2.725 Kelvin, released when the universe was only 380,000 years old. That microwave shell forms a luminous boundary at redshift about 1100. It is the farthest back light can carry information. Beyond it lies a plasma epoch opaque to photons. The ultimate edge of visibility is therefore determined by physics, not by geography. From this vantage point, the universe resembles a series of nested horizons. The nearest regions are gravitationally bound and largely immune to expansion. The Milky Way and Andromeda will eventually merge despite cosmic acceleration, because gravity on those scales overwhelms expansion. Farther out, galaxies drift apart in accordance with the Hubble constant, roughly 70 kilometers per second per megaparsec. At even greater distances, recession speeds exceed light in effective terms. Beyond about 16 billion light-years lies the event horizon, the boundary separating what can still influence our future from what cannot. At about 46.5 billion light-years lies the particle horizon, the present boundary of the observable universe. And at the outermost luminous layer lies the microwave background, the earliest electromagnetic chapter of cosmic history. All of these boundaries arise from the same trio of ingredients: expansion, the finite speed of light, and the passage of time. Remove any one of them and the concept of an edge changes entirely. If light traveled infinitely fast, there would be no observable horizon. If the universe were static, distances would not inflate beyond reach. If time were infinite into the past, we might see arbitrarily distant regions. But in our universe, time began in a hot dense state 13.8 billion years ago. Light moves at a fixed speed, and space expands. Horizons are the natural consequence. So when we ask where the universe ends, the answer is subtle. There is no wall where stars abruptly stop. There is no cosmic shoreline where matter spills into nothingness. The edge we encounter is a horizon shaped by causality. It is a boundary in time, defined by how long light has traveled and how expansion has stretched its path. The illusion of faster-than-light galaxies is simply the geometry of that expansion revealed across enormous scales. If you are still here beneath this expanding sky, reflecting on galaxies that drift beyond contact and light that has traveled for billions of years just to reach your eyes, type 2 in the comments. When astronomers first mapped the faint afterglow of the early universe, they expected irregularity. After all, the Big Bang is often imagined as a chaotic beginning, a violent expansion from unimaginable density and heat. Yet when the sky was carefully measured, something astonishing appeared. The temperature of the cosmic microwave background was almost perfectly uniform in every direction, differing by only about 1 part in 100,000. Across regions separated by billions of light years, patches of space that under ordinary expansion could never have exchanged light or heat, the temperature was nearly identical. This quiet symmetry became known as the horizon problem. How could distant regions agree so precisely if there had not been enough time for them to communicate? To understand the scale of this puzzle, imagine 2 points on opposite sides of the observable universe, roughly 93 billion light-years apart today. When the cosmic microwave background was released about 380,000 years after the beginning of expansion, those regions were already too far apart for light to have traveled between them under standard expansion rates. And yet their temperatures matched to within microkelvin precision. It was as though the entire visible cosmos had once been compressed into a single intimate region, sharing the same physical conditions before being pulled apart. In 1981, physicist Alan Guth proposed a radical solution. He suggested that in the first tiny fraction of a second, around 10 to the minus 32 seconds after the beginning, the universe underwent a period of exponential expansion known as cosmic inflation. During this brief interval, space itself expanded by an enormous factor, at least 10 to the 26th power. What had once been a minuscule, uniform patch was stretched into a region far larger than the observable universe we see today. In that picture, the distant regions of the sky were once close enough to share the same temperature and physical properties. Inflation did not allow them to communicate across billions of light years. It made them neighbors before pulling them apart. Inflation also explains another remarkable feature of the cosmos: its flatness. According to general relativity, space can be curved by matter and energy. Without inflation, even tiny initial curvature would have grown more pronounced over billions of years. Yet observations show that the geometry of the universe is astonishingly close to flat. Measurements constrain curvature to well under 1%. Inflation acts like a powerful smoothing mechanism. Just as the surface of a balloon appears flatter as it inflates, the rapid expansion diluted any initial curvature, leaving space nearly Euclidean on observable scales. The evidence for this calm geometry comes from detailed measurements of the cosmic microwave background by missions such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite. They confirmed that the background radiation follows an almost perfect blackbody spectrum at 2.725 Kelvin. That number is not approximate in spirit but precise in measurement. The spectrum matches the theoretical curve expected from a universe that began hot and dense and then cooled as it expanded. It is one of the most exact confirmations of cosmological theory ever achieved. Yet the microwave background is not perfectly smooth. Those tiny fluctuations, the variations of 1 part in 100,000, are the fingerprints of quantum fluctuations from the earliest moments. During inflation, microscopic quantum uncertainties were stretched from subatomic scales to cosmic proportions. What began as minute variations in energy density became the seeds of structure. Over billions of years, gravity amplified those slight differences, drawing matter into clusters and filaments spanning tens and even hundreds of millions of light years. The vast cosmic web of galaxies, with its glowing clusters and dark voids, traces back to those faint ripples imprinted on the sky. There is a quiet beauty in that realization. The grandest structures in existence emerged from fluctuations smaller than an atom, magnified by inflation and shaped by gravity. The calm sky we observe today hides a dynamic origin. Beneath its uniform temperature lies a history of rapid expansion, quantum uncertainty, and gravitational growth. The universe appears smooth and gentle, yet it carries within it the memory of extraordinary transformation. Inflation, however, addresses only the beginning. It explains why the early universe appears uniform and why space is nearly flat. It does not determine how expansion evolves forever. For billions of years after inflation ended, gravity slowed the rate of expansion. Matter pulled against the stretching of space, and cosmologists once assumed that this deceleration would continue indefinitely. The question was whether gravity might eventually halt expansion altogether or merely slow it. That expectation was overturned in 1998, when observations of distant Type Ia supernovae revealed something unexpected. These exploding stars serve as standard candles, allowing astronomers to measure cosmic distances with remarkable precision. When two independent research teams compared their brightness to their redshifts, they found that the supernovae were dimmer than predicted. The simplest interpretation was profound. The universe's expansion is not slowing down. It is accelerating. This discovery introduced a new dominant component of the cosmos, now called dark energy. According to current measurements, dark energy accounts for roughly 68% of the total energy density of the universe. Ordinary matter, the atoms that form stars, planets, and living beings, contributes only about 5%. Dark matter makes up around 27%. But dark energy is the largest share, and its effect is to drive space to expand faster with time. So the same cosmos that began with an explosive burst of inflation now experiences a quieter but persistent acceleration. Inflation shaped the earliest fraction of a second. Dark energy shapes the distant future. Between these two eras lies our present moment, suspended in a balance that allows us to observe both the ancient microwave glow and the accelerating drift of galaxies. The acceleration discovered in the late 20th century reshaped our understanding of cosmic destiny. For decades, the dominant expectation had been that gravity, acting over immense distances, would gradually slow expansion. Galaxies would continue to drift apart, but ever more gently, as matter pulled on matter across the vastness. Instead, the supernova measurements revealed that expansion began speeding up several billion years ago. Something subtle yet powerful was overcoming gravity on the largest scales. That something we call dark energy, though the name describes its mystery more than its nature. Dark energy does not behave like matter. Matter clumps, forms galaxies, binds into stars. Dark energy appears smooth and uniform, filling space evenly. Its defining feature is pressure, but not the familiar pressure of gas or radiation. It exerts a negative pressure, meaning that as space expands, dark energy does not dilute in the same way matter does. In the simplest model, its density remains constant even as volume increases. That constancy has extraordinary consequences. As the universe grows, matter becomes more diluted, while dark energy remains steady. Eventually, dark energy dominates completely, driving expansion ever faster. You can imagine space as a vast elastic fabric. Gravity acts like weights pulling inward, trying to slow the stretching. Dark energy behaves like a built-in tension in the fabric itself, gently but persistently pushing outward. Over billions of years, that outward tendency wins. The acceleration is not explosive. It is gradual and smooth. Galaxies do not feel a sudden shove. Instead, the distance between distant clusters increases at an ever-growing rate. The effect becomes noticeable only across immense scales of tens or hundreds of millions of light years. The consequences for the future are profound. There exists a cosmic event horizon, a distance beyond which events occurring now will never influence us. As expansion accelerates, more galaxies cross that boundary. Their light emitted today will never reach our location, no matter how long we wait. Over trillions of years, observers in our region of space will see fewer and fewer external galaxies. Eventually, only the gravitationally bound remnants of our local group will remain visible. The broader cosmic web will slip beyond sight, carried away by accelerating expansion. And yet, at this moment in cosmic history, we inhabit a uniquely privileged era. The universe is about 13.8 billion years old. The observable region spans roughly 46.5 billion light-years in every direction, forming a sphere about 93 billion light-years across. Within that sphere, we can trace nearly the entire history of cosmic evolution. We see the microwave background from 380,000 years after the beginning. We observe galaxies forming a few hundred million years later. We watch stars ignite, merge, and die. We measure supernovae revealing acceleration. We are positioned at a time when the sky still contains evidence of both inflation and dark energy. There is something quietly poetic in that timing. Inflation left its imprint as minute ripples in the microwave background. Dark energy reveals itself through the slow dimming of distant supernovae and the large-scale distribution of galaxies. One force shaped the first instant, smoothing and stretching space beyond imagination. The other shapes the far future, ensuring that expansion will not reverse but continue. Between these two accelerations lies the long era of structure formation, when gravity sculpted matter into stars and galaxies. We live during that middle chapter, when the universe is complex, luminous, and still richly connected. Despite its accelerating growth, the universe appears calm. The microwave background is uniform to extraordinary precision. On the largest scales, galaxy distributions average out to near homogeneity. There are no vast preferred directions, no giant asymmetries dominating the sky. The cosmos seems balanced and steady, but beneath that apparent stillness lies restless geometry. Space itself stretches. distances increase, horizons form and recede. The calm sky is not static. It is dynamic, evolving with each passing second. The concept of inflation and the presence of dark energy together reveal a universe governed by geometry more than by force in the traditional sense. The expansion is not matter flying into emptiness. It is the metric of space changing. Inflation was a brief, explosive change in that metric. Dark energy is a sustained, gentle change. Both are expressions of how space-time responds to energy and pressure. The equations of general relativity allow for such behavior, but their physical origin remains partly mysterious. We can measure the parameters with increasing precision, yet the deeper cause remains elusive. This brings us to a subtle philosophical threshold. The edge we seek in the universe is not a wall of stars nor a final boundary of matter. It is a horizon defined by light and time. Similarly, the limits of our understanding are not barriers in space but frontiers in theory. We know the temperature of the microwave background to 3 decimal places. We know the fraction of dark energy to within a few percent. We can calculate how quickly expansion accelerates. Yet we do not fully know what dark energy is, nor what triggered inflation. Our knowledge is precise and incomplete at once. Perhaps that is the final calm revealed by the cosmic sky. The universe is measurable, describable, mathematically consistent, and yet it retains mystery at its core. Inflation explains uniformity but leaves open the mechanism. Dark energy explains acceleration but leaves open its essence. The sky above us appears gentle and smooth, but it encodes the memory of extreme expansion at the beginning and promises isolation in the far future. We stand in the narrow middle, able to see both directions in time, aware that our horizon is vast yet finite. To appreciate how unusual our moment truly is, consider the balance of energies across cosmic time. In the earliest fraction of a second, inflation dominated completely, driving space to expand faster than any ordinary matter could influence. Then inflation ended, and its energy transformed into radiation and particles, filling the universe with a hot plasma. For hundreds of thousands of years, radiation controlled the expansion rate. As the universe cooled, matter gradually took over. Gravity began gathering material into the first stars and galaxies. Billions of years passed under this matter-dominated era, a long Middle Age when structure blossomed. Only relatively recently, about 5 billion years ago, did dark energy become strong enough to reverse gravity's slowing influence and begin accelerating expansion again. We live precisely in this transitional epoch, after structure has formed but before acceleration has erased most of the observable cosmos. That timing is not trivial. If intelligent observers had arisen billions of years earlier, they would have seen a denser universe with fewer mature galaxies and less chemical complexity. If they arose trillions of years later, they might see only a single merged galaxy, surrounded by darkness with no visible evidence of cosmic expansion at all. The microwave background would have stretched to wavelengths so long it would be nearly undetectable. The distant galaxies we now measure would have crossed beyond the event horizon. the clues to the universe's beginning would fade. In that distant future, cosmology might appear impossible, as observers would lack the data we now consider fundamental. But for us, the sky still tells its story. The microwave background remains visible at 2.725 Kelvin, filling every direction with ancient light. The pattern of its tiny temperature variations still matches the predictions of inflation with remarkable accuracy. Those variations are not random noise. They are structured in a way that reveals the density of matter, the amount of dark energy, and the geometry of space. By analyzing the angular scale of the ripples, cosmologists determine that space is nearly flat. By studying their relative heights, they infer the composition of the universe. It is as though the infant cosmos left behind a carefully encoded blueprint. Dark energy, though invisible, leaves a different signature. It shapes how galaxy clusters form and how quickly distances grow. Its influence can be measured through the brightness of distant supernovae, through the distribution of galaxies across billions of light-years, and through subtle distortions in light caused by gravitational lensing. These measurements converge on a consistent picture. Expansion accelerates, and dark energy dominates the cosmic budget. The simplest explanation is a cosmological constant, a constant energy density intrinsic to space itself. Yet more complex possibilities remain open. Dark energy could vary slowly over time. It could reflect a deeper modification of gravity on enormous scales. Each possibility carries different implications for the ultimate fate of the universe. If dark energy remains constant, expansion will continue accelerating forever. Galaxies not gravitationally bound to us will recede faster and faster, eventually vanishing from view. Star formation will slow as gas is consumed. Over trillions of years, stars will burn out, leaving remnants. White dwarfs, neutron stars, black holes. The universe will grow colder and darker, approaching a state sometimes called heat death, where usable energy becomes scarce and structure decays. This scenario is not dramatic in the sense of explosions. It is gradual, silent, and patient. Distances grow, light redshifts, temperature declines. Yet the calmness of this projected future mirrors the calmness of the microwave sky. At both ends of cosmic history, there is an appearance of smoothness. Inflation smoothed the early fireball into near uniformity. Dark energy will smooth the future into isolation. In between, gravity briefly carved complexity from slight asymmetries. That arc gives the universe a narrative shape. Rapid expansion, gradual structuring, renewed acceleration. The beginning and the end are dominated by forms of expansion. The middle, where we exist, is the era of luminous structure and complexity. This perspective reshapes how we think about edges. The universe does not present a physical boundary where matter stops. Instead, it presents horizons defined by expansion and time. Inflation pushed distant regions beyond each other's reach in the earliest instance. Dark energy continues that separation today. The observable universe is therefore a temporary window, defined by how far light has traveled since transparency and how expansion has stretched distances during that journey. The edge of what we see is not permanent. It evolves. Each year, our observable sphere grows slightly as more light arrives. Yet at the same time, the event horizon ensures that some regions are lost forever. The interplay between knowledge and limitation becomes central here. We can calculate the age of the universe to within a fraction of a percent. We can estimate the fraction of dark energy with impressive precision. We can reconstruct the timeline from fractions of a second after expansion began to the present day. And yet the deeper origin of inflation and the true nature of dark energy remain unknown. These are not gaps due to lack of data alone. They touch on the foundations of physics itself. To understand inflation fully, we may need a quantum theory of gravity that unites general relativity with quantum mechanics. To understand dark energy, we may need insights into vacuum energy or entirely new fields. The calm of the cosmic sky therefore conceals both clarity and mystery. We see a nearly uniform background radiation. We measure an accelerating expansion. We map a vast 93 billion light-year sphere of visibility. Beneath these measurable facts lies an open horizon of theory. The final edge may not be a physical limit in space, but a conceptual boundary in understanding. The equations guide us far, but they do not yet reach the ultimate origin of expansion or its ultimate cause. We drift in a universe that is mathematically elegant, observationally precise, and still quietly incomplete. If we step back and view the entire arc of cosmic history at once, a striking symmetry emerges. In the first infinitesimal fraction of a second, inflation drove space apart with unimaginable speed. In the far future, dark energy will drive space apart with quiet persistence. The early acceleration was violent and brief, magnifying quantum fluctuations into the seeds of structure. The late acceleration is gentle but relentless, gradually isolating galaxies across ever-widening distances. Between these two expansions lies the luminous era of stars, planets, chemistry, and consciousness. We inhabit that narrow middle, suspended between two accelerations that define the beginning and the end. Inflation solved more than the horizon problem. It also addressed the flatness problem and the absence of exotic relics that older cosmological models predicted. Without inflation, the density of the universe would have needed to be fine-tuned with extraordinary precision for space to appear so close to flat today. A slight excess of density would have caused rapid recollapse. A slight deficit would have led to extreme curvature. Inflation stretched the geometry so dramatically that any initial curvature became negligible on observable scales. It effectively reset the cosmic balance, leaving a universe that appears finely tuned not by coincidence, but by dynamical evolution. The quantum fluctuations stretched by inflation were tiny variations in energy density, but their imprint remains measurable in the microwave background. When cosmologists analyze the statistical distribution of temperature and isotropies, they find a pattern consistent with fluctuations that were nearly scale invariant, meaning similar in strength across a wide range of sizes. This subtle feature aligns with simple inflationary models. The agreement between theory and observation is so precise that it suggests inflation is not merely a speculative idea but a deeply embedded part of cosmic history. Yet the field responsible for inflation, sometimes called the inflaton, has not been directly observed. Its identity remains uncertain. Inflation fits the data beautifully, but its fundamental origin is still hidden. Dark energy presents a similar duality of clarity and mystery. Its effect is measurable in the large-scale structure of the universe and in the brightness of distant supernovae. Its contribution to the total energy density is inferred from multiple independent observations that converge on the same value, close to 68%. The simplest interpretation is that empty space itself possesses an intrinsic energy. In the language of general relativity, this appears as a cosmological constant, a term Einstein once introduced and later set aside. Now that term seems to describe the dominant ingredient of the cosmos. But if dark energy is vacuum energy, theoretical calculations from quantum field theory predict a value vastly larger than what is observed. The difference between prediction and measurement is enormous, one of the largest discrepancies in all of physics. This tension reminds us that even when observations are precise, interpretation can be incomplete. We measure acceleration, but we do not fully understand its source. We confirm flatness, but we do not know why inflation began or ended. The universe appears calm and uniform at the largest scales, yet beneath that calm lies a profound gap in knowledge. The geometry is smooth, but its underlying cause remains partly veiled. And yet there is something deeply reassuring in the calmness itself. The cosmic microwave background does not show wild asymmetries or violent turbulence on large scales. The distribution of galaxies, when averaged across immense distances, approaches homogeneity. The laws of physics appear consistent across billions of light years. There are no signs that the universe behaves differently in distant regions. This uniformity allows us to extrapolate from local measurements to cosmic scales. It allows cosmology to function as a science rather than as a collection of isolated observations. Between inflation and dark energy lies the present horizon, about 46.5 billion light-years in every direction. Within this sphere, light has had time to reach us since the universe became transparent. Outside it, space may continue indefinitely, perhaps even infinitely. Inflation suggests that what we observe could be only a tiny patch of a much larger whole. If inflation stretched a small region to cosmic scales, then beyond our horizon there may be regions with similar properties extending far beyond sight. The observable universe is not necessarily the entire universe. It is simply the region from which information has arrived. Dark energy ensures that this horizon will never encompass everything. Even as time passes and new light reaches us, the event horizon defines a deeper boundary. Regions currently too distant will remain forever out of contact. The expansion rate guarantees that some parts of the universe are causally disconnected from us now and forever. Our knowledge is bounded not by curiosity but by the structure of space-time itself. Perhaps this is the most humbling aspect of modern cosmology. We can measure parameters with astonishing accuracy. We can reconstruct events from fractions of a second after the beginning. We can project the future across trillions of years. Yet the ultimate edge is not something we can travel to or observe directly. It is the limit imposed by horizons and by incomplete theory. The calm sky above us is not the surface of a container. It is the visible cross-section of a far grander geometry, one that began with explosive inflation and now drifts under the influence of dark energy. In that sense, the edge is neither a cliff nor a wall. It is a meeting point between what light can reveal and what remains beyond reach. It is the boundary between measured reality and theoretical speculation. Inflation and dark energy frame that boundary. One explains why the sky is so smooth. The other explains why galaxies drift apart ever faster. Together they tell a story of a universe that expands at both its birth and its dusk, leaving us in a luminous interval where structure, awareness, and inquiry are possible. When we place inflation and dark energy side by side, the universe begins to feel less like a static stage and more like a breathing geometry. At its birth, space expanded so rapidly that distances doubled again and again in fractions of a fraction of a second. That expansion smoothed irregularities, flattened curvature, and stretched quantum fluctuations across cosmic scales. Billions of years later, after stars had formed and galaxies had assembled into filaments spanning tens of millions of light years, a different form of acceleration emerged. Dark energy, subtle yet dominant, began to push space apart ever faster. The early universe expanded with explosive intensity. The late universe expands with quiet persistence. Both are expressions of spacetime responding to energy in ways that challenge ordinary intuition. The remarkable calmness of the cosmic microwave background remains one of the clearest windows into this story. Its temperature, 2.725 Kelvin, is nearly identical in all directions. The tiny ripples imprinted upon it are not signs of chaos but of order at the smallest scale. Those ripples correspond to differences in density so slight they are measured in microkelvin, yet they determined where galaxies would eventually form. Without them, gravity would have had no foothold. The universe would have remained a nearly uniform sea of hydrogen and helium, forever dark and structureless. Inflation amplified those minute quantum variations just enough to create contrast, but not so much as to produce disorder. It balanced smoothness with imperfection, allowing complexity to arise. Dark energy now balances a different tension. Matter pulls inward. Dark energy drives outward. The competition determines the fate of cosmic expansion. Current measurements indicate that dark energy will continue to dominate, causing the scale of the universe to grow exponentially over immense spans of time. Galaxies not bound by gravity will recede beyond the event horizon. The observable sphere that today spans about 93 billion light-years will gradually become emptier as distant clusters fade from view. The night sky of the far future will be darker than ours, stripped of the rich tapestry of galaxies we can still observe. And yet, from our present vantage point, the sky appears tranquil. There is no visible tearing of space, no dramatic acceleration perceptible to the eye. The motion is detectable only through careful measurement of redshifts and luminosities. The acceleration is encoded in data, not spectacle. That subtlety is part of what makes cosmology so profound. The most powerful forces shaping the universe operate silently, detectable only through patient observation and precise mathematics. Between the explosive birth shaped by inflation and the expansive future driven by dark energy lies our fleeting present. We are able to see the cosmic microwave background, the faint relic of the first light. We can measure the clustering of galaxies and trace the scaffolding laid down by primordial fluctuations. We can detect the accelerated drift of supernovae billions of light years away. Our moment is uniquely positioned to witness both the imprint of the beginning and the signature of the future. In a deeper sense, we inhabit the only era when the universe's full narrative is still visible. The idea of an edge transforms under this perspective. The universe does not end in a boundary of matter. Instead, it reveals limits defined by time, expansion, and understanding. The observable horizon marks the distance light has traveled since transparency. The event horizon marks the distance beyond which light emitted now will never reach us. Beyond both lies a vast continuation of space-time, perhaps extending without bound. Inflation suggests that what we see may be only a small patch of a far greater whole. Dark energy ensures that we will never see all of it. This interplay between revelation and concealment gives the cosmos its quiet depth. Every measurement we make sharpens our understanding of how space stretches and how energy shapes geometry. Yet each answer opens further questions. What field drove inflation and why did it end? What is the true nature of dark energy? Is it constant or does it evolve? Are these two accelerations related in some deeper framework we have not yet uncovered? The equations describe behavior with precision, but the ultimate explanation remains just beyond reach. Perhaps the final edge is not a place in space, but the boundary where explanation meets wonder. The cosmic microwave background shows us a universe astonishingly uniform, varying by only 1 part in 100,000. Dark energy shows us a universe accelerating toward isolation. Between these truths lies a geometry both elegant and restless, stretching distances, shaping structure, and defining horizons. The sky appears calm, almost gentle, yet beneath that stillness space itself is dynamic. If you have drifted this far through the story of inflation, dark energy, and the quiet geometry of the cosmic sky, then you have crossed billions of years in thought. We stand within a 93 billion light-year sphere of visibility, aware that it is neither the whole of existence nor a closed container. It is a window opened briefly in cosmic time. The universe does not present a final wall. It offers horizons and questions. And at that meeting point between measurement and mystery, where equations describe the stretching of space-time and yet leave its deepest causes unresolved, we find not a boundary of matter but a limit of comprehension. If you are still here, still drifting among these expanding distances, type 3 in the comments and let me know you are traveling through this calm and restless cosmos with me.